Okay, so I'm going to talk about 140 word break 2, which is a follow-up to 139 word break. I did a video about 139 a few weeks ago. Check out the link over there. So let's quickly summarize what these two questions are asking. We have an input string S and a dictionary of words. What we need to do is to shatter the string S into little pieces, where each little piece is a word in the dictionary, and those pieces are a continuous chunk of the input string S. So for 139, it's a feasibility question, so we just determine whether it's true or false that we can do so. So you can see that as long as we can find a way of doing that, we can return true. But for 140, we need to return all the possible ways of segmenting the input string into different words with empty space padded in between. So let's look at the example. We have cats and dog, and the dictionary words are cat, cats, and sand. So you can see that it depends on whether you want to put S to the end of cat or beginning of and. You have multiple ways of doing the segmentation. So the result is a list of 2 ways of doing the segmentation. So as real world interview kind of settings, you code up the solution to 139. Then after the follow-up is given, there should be just some modification to the code to have that work with 140. So I'm just gonna do that today. Just quickly summarizes the solution to 139. There's the solution that I coded up is a DP dynamic programming solution. Basically, we have a DP table, which is a 1D array. You can think of this as a function can break I, which just tells us can we break S from the beginning towards the I's location, with that I be inclusive. So if we look at the third, what's this number? 3? Yeah, 3. If we look at the 3's entry in there, that was cat. So it tells us that yes, cat is a valid word in the dictionary. So in the end, we just want to grab the very last item that tells us whether we can break the full sentence from the beginning towards the end. And the code is for every location in the array that we're doing a linear scan from left to right. We look back to see the previous breakable points and check the stuff that's in between the current point and the last breakable point. If the stuff in between is a valid word, then we can build upon the previous breakable solution and just have that new word added to that solution. That makes the current location to be breakable. So that's pretty much the code here. I do have a correction to make. Last time I said this solution is going to be square time, but I think it should be cubic time on second thought. The reason being that the string slicing here in Python creates a copy. So in the worst case, the last location, last breakable point is the 0th index, where empty space is always breakable by empty space, and the current location, which can be the very last location in the sentence. So making a copy of the full string in the worst case, takes order of n time. And also, computing a hash from the string of length n, you shouldn't really treat that as a constant, I guess. So, but that string slice alone is gonna increment the time to be cubic time. So I just have a quick, correction to make about that. So let's copy the code to this second question, to be more realistic about this. As an interview setting that we are trying to modify the code to solve a follow-up. The quick note here is that the variable name is a little bit too long, so we're gonna change that can break to DP. So yeah, it looks a little bit cleaner. So in the last time that what we store in this DP table is the true or false flag, whether we can break the sentence input string until that location. Now, since that we are asking about all the possible ways of doing this break, we can just modify this as a high-level design there now. So instead of a Boolean flag for whether we can do so, we actually store all the ways that we can do the break. Instead of a Boolean in each slot in this DP table, 1D table, now it's going to be a one-dimensional. Now it's going to be a list of strings, which every string is a candidate ways of breaking the whole thing. So I'm going to just comment this out, and so that you can see what's actually being modified to get it working. So now just make modifications according to the definition change. So it says that we are storing multiple ways. We're using a list. And in the very first location, when we try to break the empty string, the only way to do so is by using a empty string. So that's our base case here. What we're gonna do is we're gonna grab this to avoid making multiple copies on the fly. So we're just gonna use this. So if we at this current location, we look back to find the last breakable point, which is a list of non-empty stuff in them. That's the multiple different ways of breaking the sentence input string until the previous breakable point. What we're gonna do is just test the word at just the same logic as the last time. And if it's a valid word, we're just gonna append that word to every possible solutions that we retrieved from the previous breakable points. So we're just gonna extend this to be the candidates plus empty string plus the current word. If the candidate is it's not the initial case, base case. Otherwise, we just directly put that word there. So this handles the case. This if else here handles that when we first, very beginning in the scanning, when we find the cat here at the third location. So we don't want to add an extra space in there. Since that it's now a dictionary now, we don't have the negative one to access that, so we have to use the n here. So with this modification, I think it should work. It's exactly as what's being described here, and the modification is just a changing of the content in there. So let's try. Yeah, it's working. A big problem of this is gonna be that let's analyze the time and space complexity before we go. So the time complexity is gonna be even though it's not super obvious by looking at the code, it's actually gonna be 2 to the n-1. So it's basically that between every character in the input string s, it's a valid point that we test whether it's breakable or not. So the worst case input would be something like we're gonna use examples to demonstrate. I think it's a little bit easier. So S, let's say that it's 4 different A's, and the dictionary it's the string. Is this, then how many ways can we actually break the string S with this dictionary? It's actually 2 to the third. It's 8. So let's actually just popping it out. So you just quickly go through this worst case kind of a scenario when you have input string S to be something like this, and the word dictionary to be in this case. It's as bad as it could get, almost. So there are 1, 2, 3, 4, 5, 6, 7, 8 different ways of segmenting the input string into a list of words using the dictionary, and there are n-1 breakable points inside the input string, and in this case here, every point is possible a breakable point. So that the solution, the time and space, is 2 to the is this number 2 to the n-1 for both time and space. For time, you have to test all the possibilities. For space, it's actually, I think it's n multiplied by that. Because each of this is it's of it's all length at least n. So that's time, and this is space. That's not counting the intermediate step memories. So what's really bad about this here is that what if we have something like a B? We're gonna store everything something like this at the last but the DP, this is gonna be what we store at the DP 1, 2, 3, 4. DP4 is gonna equal to this thing. If we have one extra B in there, even though it's not breakable, we're gonna accumulate a lot of stuff in the way that we're searching through the way. So it's this is I think it's essentially breadth first search. All the levels we store the candidates, which is kind of wasteful. And I guess one quick way to solve this, kind of relieve this problem, is to a certain degree, is to maybe just uncomment this part, do a quick check whether we can actually do the break or not. If it's not breakable, then we don't go about and accumulating all this intermediate result in there. So we're gonna just change this. So if it's not breakable, we don't bother about collecting all those intermediate results and try to build out the candidates, which is going to return empty stuff. Otherwise, we would try to actually do this kind of level by level traversal through all the possibilities and do that. So it should working exactly the same way. It's just that we can have an early stopping if the stuff is not breakable. So compared to the 2 to the n exponential time, this is cubic time, so it's not too bad. And yeah, so this is do a quick check whether we can do the break or not, and then once we have checked that, we did indeed want to go about and build out all the candidates, all the solutions. We go about do that. So let's try submit this. Okay, it's working. Not too fast. Okay, so let's talk about some of the even more about some of the follow-ups. One thing that we can actually do here to potentially help is when we try to find the last breakable points. If we can just do a test of the maximum length of the vocabulary here, we no longer need to go from 0 to the current location. We can just test go back to as far as the maximum possible word length in there. So that could potentially save a little bit here, and also that once we pass certain point, we can actually discard some of the DP stuff in this in the table, because since that we no longer need to consider those last breakable points once we surpass certain location, certain distance, we can actually discard those to save some memory. That's also some quick modification we can do. I guess another way to do so is to actually just code up a DFS solution, a DFS kind of backtracking solution. That way you really save a lot of space. Basically, it's trying to go as far as possible, as DFS, to come up with a solution towards the end. If that doesn't work, then you go backtracking. The intermediate result that being stuffed in the memory is going to be very much less than this one that we have. For maybe with some pruning, this can be okay. Yeah, the space is pretty bad. Time is not fast, but at least there are just pinpoint surround some ideas of further optimization, which you can do at the interview time. So that's the question for today.